Hello and welcome back, my dear students. Today, we're taking our exploration to the next dimension. Literally, I mean it. We're moving from only simple planes and lines to curved surfaces, to surfaces in the three-dimensional space. So if you start to think about anything around you, I need you just to look around you. Look at all of these 3D objects around you. What do you see? Let's say that you have a sphere, a ball. I need you to think about this ball. If you try to slice this ball, okay, from anywhere, vertically, horizontally, anywhere, what you're going to get? You're going to get a circle. So these slices, when we slice it, we call it the conic section of that three-dimensional space. And basically, if I need to graph any three-dimensional space, the easiest way to do it is by getting their conic sections. Maybe it could be a line, an ellipse, parabola, or hyperbola. Then after I graph the three conic sections, or what we're going to call later on traces, then graphing the three-dimensional space will be very simple. So if you think about, let's say, this cone. If you have a cone and we try just to cross-section that cone horizontally, so what do we get? The cross-section will be basically an ellipse. And if I see the shape in the two-dimensional space, this is from now on, we're going to call it a trace. We will have two types of surfaces to cover in this section. The first type of surfaces is what we call cylinder surfaces. So a cylinder surface is basically made out of all possible lines that we're going to call rulings. These lines are parallel to a given line. There's a given line and these lines should be parallel to that one. And they should pass through a given plane curve. How do I know if the surface given is a cylinder? Usually the idea of cylinders that they give you an equation, okay, with one missing variable. So, okay, you have the equation with two variables only, but you need to graph it into the three-dimensional space. Okay, if there's two variables, one missing, so this is a good indication that this surface could be a cylinder. Now let's try one example and see what do I mean by that. Let's say we have this example. I need to draw a graph of the surface of z equals y squared, okay, in the three-dimensional space. So if you look carefully at the equation, you'll notice that it's what? It only has two variables only, and we miss the x variable, okay? So that it doesn't include the x variable, which means that x is arbitrary, all values. So how do I think about this one? I'll think about it as z equals to y squared. So let's use, okay. So I think about it as z equals y squared. And this parabola, this is basically a parabola. And this parabola is moving along the missing axis, which is the x-axis. So I have the line as x equals to k, okay, which is a scalar, okay, where k could be any real number. So k is any real number. So now what do we have? They give me a surface equation. It has only two variables, z and y. We miss the third one, which is x. So anytime you have two variables and you miss the third one and you need to graph it in the three-dimensional space, so this should be a cylinder surface. Now, z equals y squared is a parabola. And you need to let the missing variable as your scalar, the line that it's parallel to. So x equals to k, where k could be any real number, which is a scalar. Now, how do I graph it? I start by graphing the parabola. Just like roughly, let's try to graph z equals y squared. So it should be between what? We need to graph it along the x-axis. X-axis, it changes. So I have, let's think about it as you have many parabolas, okay? So let's think that we have a parabola here, another parabola there, one more. You have many, many parabolas. And all of them, we graph them along the x-axis. And I have something there. You have many, infinitely many parabolas that you graph them along the x-axis. If I think to join these parabolas, okay, I'll try just to make it as clear as possible. So these supposed to look like something like this, just to show that this is okay. So this shape here, the one that I got here, looks like a parabolic cylinder. This is shape here. This is what I call a parabolic cylinder. Okay. So the idea, you have two variables. The third one is the axis that where we graph it along with many, many parabolas, and then I join them with a 3D shape, and this one is the parabolic cylinder. It looks something like this. If I do the graph like more accurate using any computer graphing program, you'll get something like this. So it's many, many parabolas, so it looks like this in the 3-dimensional space. Let's try another equation. Something like this. So what do I have here? I need to graph the surface of x squared plus y squared equals to 4, again in the 3-dimensional space. So this is an equation of what? This is a circle. Okay, with center 0, 0 and radius 2. What's the missing variable? We miss z. So I need to say that z equals to k, which is where k belongs to r, any real number. And this is basically a scalar. So what do you think we'll get in this case? So if I'm trying to graph a circle with center 0, 0 and radius 2, okay, and it involves only x and y, okay? So I'll come to x and y, both of them. I'll take 2, negative 2, 2, negative 2. Same thing for x, 2, negative 2. And I'll try to join them with a circle. I'll try just to make the best fit. Always it's good for the back side, just to be dashed and it looks smaller. This is the behind one. So this is something like this. We have this circle almost. Now I need the third side. So I have many, many circles on top of each other along the z-axis. So you'll have another circle, let's say here, and another circle up, and one additional circle down. You have many, many circles with radius 2 on top of each other. So if I join them all, okay, so I'll get what looks like a cylinder. So this looks like a 3D shape, which is basically a cylinder with radius of 2. Okay, so this is the idea behind the cylinder surfaces. Hopefully this is clear idea. Now we'll move to the quadric surfaces. For the quadric surfaces, the general equation has all the 3 variables, so we don't miss any of them. So we have x and y and z. In general, the equation looks something like this. This is the general form. So it has x squared, y squared, z squared, xy, yz, xz, and xyz, and the constant term. Sometimes we have some of them equals to 0, some they don't, but they are not all of them equals to 0. Notice, in general, these graphs, the quadric surfaces, they are all coming back to the idea of they are the traces of a conic section. So if you think about this double cone here, that's why they call them the conic section. It's coming the idea from a cone. So it depends how do you slice it and what do you find. You see the first one, when I slice it like horizontally, this time we got a circle. If we do it a bit with a slope, I'll get an ellipse. In this way, we'll get a parabola. If I do it totally vertically, so I'll get a hyperbola. So these are the 4 options that we may get when we have our conic section. Now you see, just we need some of these conic sections. That's why I added for you the coming 2 slides, just to remind you of the standard form of equations for these conic sections. Starting from circle, which is, you should be familiar with circle. We've used it a lot, this term. Also with ellipse. This is the general form of the hyperbola. Notice the difference. It looks like the ellipse equation, but notice the difference. With the ellipse, the operation in between is addition. With the hyperbola, there is a minus in between. And the parabola, which you already know very well. So maybe the only one that we didn't use a lot this term is the hyperbola. So the equation looks exactly like the ellipse. The only difference is the sign in between. It has a negative sign. And as you see, sometimes it changes if it's like we graph it parallel to the x-axis or to the y-axis. These 2 forms. It depends which one is negative, by the way. Okay. Now, till the end of this section, we're going to explore how to graph all of these 6 quadric surfaces, from ellipsoid, elliptical paraboloid, hyperbolic paraboloid, cone, hyperboloid of 1 sheet, and hyperboloid of 2 sheets. It's very good just to make yourself just familiar with all of these general equations. So I need you to practice, okay, in case that you have any question as a matching question, you need to recognize the equation once you see, or recognize the surface once you look at the equation. So let's try just to learn a little bit about the equations before we start diving in one by one. So the first one we're gonna just work out is the ellipsoid. So if you think about the ellipsoid, I need you just to imagine that you're slicing the ellipsoid, okay? Anyway, you're slicing it along the y-axis, the z-axis, the x-axis. From any way, you're gonna get an ellipse. So all the traces for the ellipsoid are ellipses. If all of the denominators here are a, b, c, they are equals to each other. So this is a special case. Now I don't have ellipses. I have the traces as circles. So what could be the result in the 3-dimensional space? It should be a sphere. So the sphere is basically a special case of the ellipsoid, when the traces are circles, not ellipses. Now see the general form of the equation, which I need you to consider now. What do we have here? We have the equation as all of them squared, okay? All of them positive, and we have a constant term here. So this is a good way to recognize the equation that it's an ellipse. So all squares, all positive, I have a constant term here. Okay? Now, moving to the second style of equations, the second type of equations. Let's think about the cone. What do we have in the cone? I prefer always to put all variables in one side. It's easier to recognize the equation. So I rewrite this equation as x squared over a squared plus y squared over b squared minus z squared over c squared equals to 0. So now this is where we need to look at the equation. So it's always good to prepare the question, have all variables in one side. Now look at this equation. I have all squared, all positive except one. Only one of them is negative. And there's no constant. It's only 0. The constant is equals to 0. So you see the difference between the cone and the ellipsoid. All squared, 1 negative equals to 0. There's no constant. It's only equals to 0. This is what we call the cone. Now, if you notice a relation now, just by looking at the equation, it's good just first to learn the equations before we start graphing. Now, I need you to think about the traces first. Think about the cone. If I take a traces horizontally, what do I get? I get ellipses, maybe circles sometimes. It depends on the values for A and B. Okay, so we try just with the horizontal cross sections, and we got clearly circles or ellipses. Remember, always when we say ellipses, it includes circles as a special case if A is equal to B. Now, if I think just to the other cross sections, the other traces, if we cross it vertically, so what we're expecting to get. So if I do any cross section vertically here as it could be like either a hyperbola, but if I take it at k equals to 0 at the center, which you look at two straight lines, so we have lines. So it could be like lines or hyperbola as a traces for the cone. So ellipses, lines, hyperbola. Now moving to the third surface, which is the hyperboloid of one sheet. Look at the equation now. We need always just to try to learn how to recognize the surface from the equation. This is really important. So what do we see? Again, it's all squared except one negative. So it's exactly like the cone one. You see the left-hand side is exactly the same. The difference is here. This is 1, in the cone it's 0. As you see in the cone, it's just like at the center, it's the point 0, 0, 0 at the origin. So if the constant term equals to 0, this is a cone. If it's other than 0, it shouldn't be always 1. Sometimes they write it in a different way, and then you write in the general form. But it's anything other than 0, so this is what we call the hyperboloid of one sheet. If I think about the traces of the hyperboloid of one sheet, so it could be either, you look at any horizontal traces, I'll get ellipses. If I do vertical traces or along Z here, I'll get hyperbolas. So it's either ellipses or hyperbolas. And the other note that I need you to be careful about, that for these surfaces, we always graph along the different variable. So these are all positive. The only different one is the negative one. So that's why you notice that we graph them along the z-axis. Now, the surface number 4 is the hyperboloid of two sheets. Look at the equation, try to compare it with what we have before. So this is the equation. Just try to compare. It has all squares, x, y, z, all of them squares. But I have 2 negative, 1 positive. 2 negative, 1 positive, and it's equals to 1. So compare it with the one with one sheet or two sheets. One sheet has 1 negative. Two sheets, it has 2 negative signs. It's always important to put all variables in one side just in order to decide what surface is this. And the variable here equals to 1. You see here, this is one sheet. It's all like one piece. And here I graph it like into two sheets. Now, where do we graph it along what? What do we have here? Most of them are negative. Only the different one is the positive one. So that's why we graph it along the z-axis. So as you see, just always we decide we graph along what? The different one. So now all of these 4 surfaces, they have all squares. Some of them, they are all have a constant term other than 0, except the cone is the only one with 0. Ellipsoid, all positive. Cone, all positive except 1. Hyperboloid of one sheet, all positive except 1, but it's equals a constant, does not equal to 0. Hyperboloid of two sheets, they are all negative except 1, so I have only 1 positive. Now we'll move to this type of surfaces. See this equation now. It's not all quadratic, you see. There's only 2 squares, 1 linear. This graph or this surface is what we call the elliptic paraboloid. If you think about the traces of the elliptic paraboloid, take anything, just cross it or slice it horizontally, we'll get ellipses, okay? Maybe circles if A equals to B. If I do the slices vertically, what do I get? Just do this way, you'll have what? A parabola. So the traces could be either ellipses or parabolas. How do I distinguish the equation? It's all squares except one. There's one linear, and the sign between the two squares is positive. Now moving to the last one. Here, this graph is what they call the hyperbolic paraboloid. Let's look at the equation. Just try to see the difference between this one and the elliptic paraboloid. This one has two squares, one linear. This has positive sign in between, this has negative sign in between. You see the difference? This is the only difference. If it has negative sign between the two squares, this is the hyperbolic paraboloid. And the traces could be what? Hyperbola or parabola. Okay? Now this is very important for you, just to try to learn how to distinguish the surface from the equation for the purposes of, let's say you check your answer one way, and the other important use for that is if the question is a matching question. So you can easily decide. And you have to learn, it's required from you just to know the name of these surfaces. Now let's start with graphing these surfaces one by one. We'll start first with the ellipsoid. So if you think about the ellipsoid again, we saw this, the standard equation. Okay, and the features, they are all positive, all of them squared. It has a constant term. All traces are ellipses, and we'll try now to graph it one by one. Okay. This is the quadric surface for the sphere as a special case of the ellipsoid. By the way, here we show the equation as a standard equation with the center of the origin at 0, 0, 0. But in this form, they show that for any center. So here the center is ABC for this ellipsoid or sphere. Okay? Now, let's start with graphing. How do we graph? What we need to do in graphing, I need just basically to find the traces. I need to determine what are the traces, and then I graph the traces. Basically, the traces are what? I need the intercept. So I need the XY plane, the intercept with the XY plane. So to find the intercept with the XY plane, I need to do what? I need Z to be equals to 0. Okay, let's try to let Z equals to 0. So this will be x squared over 1 plus, this is plane, so I need x squared over 1 plus y squared over 4 equals to 1. And this is the first trace, which is basically, if you look at the equation, this is what? This is an ellipse. Okay, try another trace. This time we'll take the intercept with the xz plane. So if I need to find the intercept with the xz plane, I need y to be equals to 0 this time. So if y is equals to 0, this cancel out the middle term. So this is x squared over 1 plus z squared over 9, and this is equals to 1. And this is another ellipse. So the second trace is another ellipse. We'll try the last one. This is the intercept now with what? We need to take the YZ plane. YZ plane. And this time I'll use x to be equals to 0. So if x is equals to 0, what should be the ellipse? So it's x0. So I have only y squared over 4 plus z squared over 9 equals to 1. And this is our last trace, and it's again an ellipse. Now to graph this ellipsoid, I need to graph these ellipses, the 3 of them. We'll start with the first one. Remember, if we graph an ellipse, we need to know the radius. So it's of the general form equals to 1. The center is 0, 0. the radius from the x-axis is 1. So it's basically you go 1 minus 1. So this is the x-axis. So I go just 1, negative 1. Y, the denominator 4. So the radius is 2, negative 2. And then you join them with an ellipse. Okay, so this is the first trace. Now I'll do the second trace. I'll use another color just to make it easier to see later on. X at 1, again, I'll use this point, 1, negative 1. Z9, so the radius is a 3, so I'll go with the z-axis 3 and down negative 3. And again, I'll join them with an ellipse. Let's try to make this. Remember, we're sketching. Nobody asked you to be super accurate. So this is the second ellipse. And lastly, I'll do the last one. Y4, so at Y it's 2, negative 2. Z9, so it's a 3, negative 3. And I'll do the third ellipse. Just joining the green points. So by joining the green points, clearly now you have an ellipsoid. It looks like a 3D shape, which is an ellipsoid. Okay, now let's try the second surface, to graph the second surface. This is, as you see, the traces that we already found. This is the by any computer graphing program, you can do that. Okay, now we'll move to the second one, which is the paraboloid. Paraboloid. How do I know it's paraboloid? It's 2 squares, 1 linear. There's addition in between. So this is paraboloid. I'm going to graph it along what? The z-axis. You see how much do I know only from the equation? Okay, we'll start with traces. The first trace, we need to get it with same thing as before, the intersection with the xy plane. So basically you need to let z equals to 0. Okay, if z is equals to 0, this is x squared plus y squared equals to 0. And this is basically what? A point. This is only this point, the origin. Okay. One point is not useful for us. So anytime you have a 0, you need to get another one. So I need to get more traces, not only 0. So I'll try to do what? I'll say let z be equals to k as a scalar, where k should be equals to what? Think about here. X squared plus y squared, this is summation of 2 squares. So z basically should be for sure greater than or equals to 0. We have already considered the case of 0. So now I need to take anything larger than 0. So let z be equals to k, where k is greater than 0. So the equation now should be what? X squared plus y squared equals to k. And this is a circle, circles even. So anytime you change k, you get a new circle. So the first trace is either we have a point and circles. Let's try the second trace. Now we'll use the intersection with the xz plane. So now I need to let y equals to 0. So what do I get if y is equal to 0? So now I have y0. So this is x squared equals to z. And this is a parabola. This is a parabola. The last one now, the third one. So I have xy, xz, now I have yz. I need the intersection with the yz plane, so I'll let x be equals to the 0 this time. So this one will be equals, x is 0, so I have y squared equals to z, and this is another parabola. So as you see now, the traces are what? If you look at the traces, so I have one point, which I already showed there, and I have many circles going along the z-axis, and I have two parabolas. Let's start with the parabolas. for graphing. So I'll do the first parabola, it's z equals x squared. So from the x-axis, but along the z. So it should be something like this. The second parabola is z equals y squared. So something like this. Now the last trace should be what? We have the point already, so there's nothing below the, or in the negative part of the z-axis. Now I need circles. So let's graph some circles along the z-axis. Notice here, there's only xy. Z is missing, so z is just only scalar. So I need to do many circles along the z-axis, just till you're able to see it as a paraboloid. Or let's say this is the last one. So as you see, just we have two parabolas and circles with a point here. So this is the paraboloid. This is the paraboloid. Okay, good. So this is the second surface. Now let's move to the third one. What do we have next? I need always to look at the equation before I decide. I need you to practice this. So I look at the equation. Remember, as I said, just I need always to let all variables to be in one side. So I need to see the equation as x squared over 1 plus y squared over 4 minus z squared over 1 equals to 0. Now this equation, from its format, it's all squared. 1 negative equals to 0. The one which is equals to 0 with 1 negative is a cone. So this is the elliptic cone. Now I need to see the traces. What are the traces for the cone? I'll start with the first trace for the cone, okay? So for the traces with the cone, I'll start, let's say, with x equals to 0. So this is the intersection with the YZ plane. What will happen if x is equals to 0? Let's see. I'll use this form of the equation. If x is equals to 0, so this is y squared over 4 minus z squared over 1 equals to 0. So is it a circle? No. There's negative in between. So I'll solve this equation for y. Y squared equals 4z squared, right? Try to solve for y. Y equals plus minus 2z. And this is what? These are lines. This is an equation of lines in this case. Okay, we have two lines. Now let's try to find the second trace. So the second trace, I'll try this time when y is equal to 0. When y is equal to 0, so this is the intercept with the xz plane. If y is equal to 0, what do you think we'll get? Let's try. Y equals to 0. So this time I have x squared equals z squared. So basically I have x equals plus minus z. So this is again lines. These are the lines that passing by the origin. X equals z plus minus. One increasing, one decreasing. Same thing here. Now let's try with the last trace. The last one we took xy, now z. Z equals to 0, so this is the trace with the xy plane, the intercept with the xy plane. Z equals to 0, so this is x squared plus y squared over 4 equals to 0. And this is again a point. Remember, as I said before, anytime you have a 0, which is a point, you need to change it with a scalar. So I need to change now. I'll say let z be equals to k. What should be k in this case? Again, it should be positive, right? One more time, just like as before, it should be positive. Okay, but anyway, it will be z squared, so it's positive anyway. So now the equation should be what? X squared plus y squared over 4 equals k squared. And this is again an equation of circles. So now what do I have? Two lines and circles. By the way, if you try even to find not only the intercept with the planes, if you try just to have the cross section with, let's say y equals to 3, y equals to a, you will find hyperbola. But no need, these are enough for us to graph it. So now I have two lines. Just let's move to the graphing part. What do I expect to get? I get a cone along the z-axis. So we have two lines, y equals 2z. So let's say that we have one line this way, the other line this way. Okay, there's two more lines, but they are like not showing. And I need many circles. So I'll graph, let's say that we have different circles. This is the point, the 0, 0, you see? This is the point. And I need circles, but the circles goes like what? It could be, since z squared, it could be plus or minus, okay. So I'll take up and down. So there's a circle above. Remember, these graphs are all extended along the whole z-axis. So it goes from negative infinity to infinity. They are non-stop. So this is basically an elliptic cone. This is an elliptic cone. You see, A and B are different, so it's an ellipse, not a circle. Okay, so this is basically the elliptic cone. Hopefully the idea so far is clear. So once you start learning about traces, the graphing of the 3D surfaces will be easy. But I need you to remember, anytime you have a point as equals to 0, notice here we didn't say a point in the previous one because it has, where's the lines? Maybe we went so much backward. Yeah, here, that's it. It wasn't the same slide. Anyway, so here when I have y squared minus z squared equals to 0, I didn't say a point. I had to solve it as a straight line. Here I said a point because this is like the form of the equation of the circle, but with radius 0. So this is like a circle with radius 0. So this is basically what? A point. Okay, so see the difference between them. So maybe you think, why it's here 0, we didn't say, just change it with k. Because I could solve it. This is a straight line. If k is equal to 0. If k is equals to 0, this is straight line. If I consider k does not equal to 0, this will be hyperbolas. I can just finish it, but it will be like y squared over 4 minus so it will be a hyperbola. Okay, we were working here. So this is y squared minus z squared equals to k. So these are the hyperbolas I talked about. But no need just to graph them. It's enough to use lines and circles. Now, let's move to the next surface. It's an interesting one. For sure you saw this surface many times before. It has many different applications in real life. What do we have in the hyperboloid? The equation will looks like all squares 1 negative equals to 1. It has a constant term, and the direction, or we graph it along the negative side, the negative variable. So we graph it in this case along the z-axis. If I think again about the traces, so I'm going to have ellipse and hyperbola. I'm going just to have ellipses and hyperbola. Okay, let's try to find the traces. This is the equation. It's already prepared. It says all squared 1 negative equals to 1. So this is the hyperboloid with one sheet. Let's try to find the traces. And we graph it along the z-axis. So this is, we graph it along the z-axis. Remember, always we decide it's along what? According to the different one. Okay. So the first time we'll do x equals to 0. So this is like with the YZ plane. The intercepts with the YZ plane. Let x equals to 0. What do you have? y squared over 1 minus z squared over 2 equals to 1. And this is an equation of hyperbola. Remember, the one which looks like a circle but with negative in between, this is the hyperbola. Try another time to take the second trace at y equals to 0, which is with the xz plane. So now y equals to 0, so this is x squared divided by 4 minus z squared over 2 equals to 1. And this is another hyperbola. This is... Let's try with the third trace, the last one. Trace number 3. So I'll let z equals to 0 this time. So this is with the xy plane. With the xy plane, try z equals to 0. So you'll have x squared over 4 plus y squared over 1 equals to 1. And this is basically what? This is a circle or an ellipse. The denominator different, so this is an ellipse. So this is an ellipse. This is an ellipse. Okay? Now let's see what can we do. How can we graph it? We'll start with the ellipse. I'll start with the ellipse. So this is the ellipse. We have at the x, we have, with the x, we have 2, negative 2. And with the y, I have 1, negative 1. Let's start with this ellipse in here. Usually we need the back one just to look smaller. So this is the first ellipse. Now to do the graphing of the hyperbola, you need to have the graph. This is the first one. So we had like 2, negative 2, 1, negative 1. I need the shape to look, I'll have some extra ellipse, another one. So let's say that we have something like here and one down there. And I need to join them with hyperbola. Something like this. Should be like bigger. And from this side, same thing. Okay, this I'm doing it like only approximately, no need just to be super accurate with the graphing. So you have the ellipse in between and another one, and then you join them with like the shapes of hyperbola. Okay? If you need just the most accurate one, it looks something like this. This is the hyperboloid of one sheet. Okay? Now the shape before the last that we have to graph it is the hyperboloid of two sheets. With the hyperboloid of two sheets, we have the equation as all squared, 2 negative, and it's equals to 1. So I need again for the hyperboloid of two sheets to find the traces. So let's try, where do we graph it along what? The different one. Remember all of these shapes, we graph them along the different one. All negative, one positive. So this is, we graph it along the x-axis. Okay, let's try to graph it along the x-axis. We'll prepare the traces. So traces. The first trace I'll take at x equals to 0 with the yz plane. And this equals to negative y squared minus z squared over 2 equals to 1. Multiply all of it by negative 1. So this is y squared plus z squared over 2 equals to negative 1. So can this be a possible case? No. This is not possible. What does it mean? That this graph will not cross the yz plane. This is not possible in this case. Okay, If it's not possible, I need to try another value. It's just like the case where we have 0. So I need to try something else. So I'll let x be equals to k. Since this is not possible, I'll try x equals to k. That means it will not cross the origin, nothing at the origin here at the middle. So I'll take x equals to k. So now the equation will be k squared over 4 minus y squared minus z squared over 4 equals to 1. Just solve this equation. This is y squared plus z squared over 4 equals to what? K squared over 4 minus 1. And this is an equation of circle. This is an ellipse. Sorry. This is an ellipse. This is an ellipse. Okay. Now to have this ellipse defined, notice that what do we need to have? Just to have it defined, I need this to be positive. I need this value to be positive. So think about this. So if I just consider k squared over 4 minus 1 to be greater than or equals to 0, so that means I have k should be greater than 2 or k less than or equals to negative 2. Okay, so it's an ellipsis, but there's a gap. It's only greater than 2, less than negative 2. So there's nothing in between. Now let's continue with more traces. Let's see what do we have. So this is only the first trace. I'll try the second one. When y is equal to 0, okay, so this is the one with xz plane. So now I have x squared over 4 minus z squared over 2 equals to 1. And this is a hyperbola. Okay, try the third one. At z equals to 0. This is with the xy plane. And at z equals to 0, we have x squared over 4 minus y squared equals to 1. So this is again should be equals to what? Another hyperbola. Okay, so now once we have all the traces ready, we'll begin graphing. The easiest way to graph, as I said here, just since there's a gap in between negative 2 to 2. So let's see these points with the x-axis. So this is 2, this is negative 2. So all of the ellipses, I'm going to see them just at k greater than 2 and k less than negative 2. So let's do the traces here. So it looks like we have the ellipses. It shows us approximately. So we have the ellipses all there. And the shape, if I do a hyperbola, so I'll have something like this here and another hyperbola. So this is the second part. So this is the hyperbola and one here, and the rest will be all ellipses. So it will look something like this. Okay. The most important part, just to show the gap, it will be between what and what. Just solve this inequality. Once we take k, we solve it between greater than 1, less than 1. And this is the last one that you have to graph. The last surface, it's not required from you to do the graphing, which is the hyperbolic paraboloid. Okay, just only try just to figure out what are the traces. So it's you have two parabola, one hyperbola, and the graph will look something. You see, these are two parabolas. If we add the hyperbola, it looks something like this. This is the hyperbolic paraboloid, and you're not required to graph it. Okay, and that's it for section 10.6, and this is the end of chapter 10. Next time we'll move to chapter 11, and we'll cover 2 sections out of chapter 11.